So our design process for many projects is very customer-led. So what we've created is a development kit where you can buy our actuator modules on assemblies that you can kind of snap together with as many actuators as you need, as many actuators sizes as you need in whatever orientation that you want at your facility with your product. And your engineering team can start to explore, what is the exact configuration of the system that best satisfies what you need to do, because ultimately you understand your product the best. You know how your product works, you know how it's presented to the robot, you know what the packaging looks like. And so when they're done doing that development process, they can then contact us and say, this is the design that we came up with, and we'll take that design and we'll convert it into a version that is very, very robust for an industrial environment. We also do our own internal gripper development for projects and problems that we're incredibly excited about. And often the way that development process works is you go to the store. So you go to a supermarket, or you go to a toy store, or you go to an e-commerce fulfillment site and start buying piles of objects. So you take the things that you just bought, you start building a gazillion different grippers, trying to see what are the grasp parameters that drive quality of the grasp. You also start playing around with the control systems that we build, the pneumatic control systems, to figure out what sort of pneumatic profiles deliver the best quality in an application. And you kind of build up from there until you have the finalized concept. So my day at Soft Robotics typically focuses on the actuators themselves. Since this is a brand new field of science and engineering, there's a lot of things that need to be worked out. So even building an actuator, a sophisticated actuator, requires inventing the prototyping methods that then create the thing that you want to even test in the first place. So that's a piece of it. Understanding how to simulate elastomers, for example, is an ever increasingly sophisticated science, and new software is coming out all the time, and it's driving the quality of the simulations, but that's a thing. And once you've done the prototyping and the simulation, and you're building a couple of parts that generate the sort of physical behaviors you're trying to create for a customer, you then need to do the process of starting to scale up to manufacturing, starting to build out what would be the bulk manufacturing processes that can create the thing that you just prototyped up in lab, and making sure that they meet all the sorts of functional and functional performance tests that you want it to have hit. So does it last long enough? Is it easily abraded? Is it easy to make? Because ultimately, unlike the stuff that people typically build in lab, you need to pump out thousands, 10,000, 100,000, millions of these actuators. So you need to be able to, drive it through that whole process. And so that's what I focus heavily on. But in order to build soft robotic systems that are sophisticated and truly satisfy a customer's needs, where in our case that typically means being able to manipulate complex objects very quickly in a way that is extremely reproducible. So the standards in industrial automation is essentially that you get it right all day, every day, all year, because otherwise you shut down a factory line, which is an incredible cost. So being able to go from hobbyist work to systems that deliver that level of precision and accuracy requires not just soft robotic actuators, but a whole marriage of systems. The pneumatics, the pneumatic control systems, the AI software, you name it. If it's in a conventional robot, it's in what we do, plus having to also understand all the different new aspects of soft actuators. Simulations are never perfect. Anyone who's run the simulation knows that. And when you run experiments, even if the experiment works, you never always completely glean everything that was relevant about what just happened. You can actually miss a lot of insights if you don't have simulation. So, doing fast iteration through simulation followed by fast iteration through experiment and marching forward like that's always best. Personally, in all the work that I do. Now, as far as simulating the industrial environment, it's very common in industry to have factory workflow simulation software, where you have your conveyor, you have your robot, you have, whatever is the process you're trying to mock up, so that you can understand all the things that are creating choke points for rates, and to create a very, very streamlined factory. And we build gripping solutions, but factories are a whole myriad of different kinds of technologies. So that's the simulation that they do. As far as the simulation that we do, for the most part, the simulation focuses heavily on the actuators themselves. So there are a lot of things that you can learn computationally about how different patternings of plastics and elastomers, or multiple different kinds of elastomers, where you have variable stiffness all over the body and other mechanical properties of materials. It's a lot easier often, or a lot more efficient, to kind of get a first pass about what that actuator is going to do in an FEA style simulation space, and then iterate from there with physical versions of the actuator, moving in increasing sophistication and how you build the actuator and how you run the simulation model. And so that creates deep insights that we worked really hard to build here, and it creates a very, very rapid development process.